Most optical imaging instruments make use of circular lenses or mirrors or circular irises. Light passing through the apertures created by these components is diffracted. Every point on an object is spread out to form a characteristic circular pattern in the image. This pattern consists of a bright circular disc, called the airy disc, surrounded by weak concentric fringes. The airy pattern can be shown as an isometric plot. The peak at the centre of the plot represents the airy disc. If the diameter of the diffracting aperture is large, then the width of the airy disc is very small, so we can distinguish image points which are very close together. But if the aperture is small, the airy disc is wide. Then close points in the image plane overlap and may not be distinguishable. The limit of resolution is defined to be the linear or angular separation between two object points that can just be distinguished as separate points in the image. For an astronomical telescope looking at stars, it is easy to think of the limit of resolution as the angular separation between two stars which are just resolved in the image. For the human eye, it might be more convenient to think of it as the closest distance between two pinholes in an opaque screen that could just be separated when looking at them closely from the normal reading distance. Either way, we need some objective definition to be able to measure it. The Rayleigh criterion states that 2 points are at the limit of resolution if the centre of the airy pattern of one coincides in position with the first minimum of the airy pattern of the other. The first minimum of the airy pattern is formed in the direction given by the equation sin theta equals 1.22 lambda divided by a, in which theta is the angle from the centre of the pattern, lambda is the wavelength of the light used, and a is the diameter of the diffracting aperture. For most telescopes, a is the diameter of the objective lens. For an instrument like this celestron telescope, the objective diameter is 200 millimeters. Assuming an average value of the wavelength of light to be 550 nanometers, the limit of resolution of this telescope should be 3.4 times 10 to the power minus 6 radians. This is a very small angle, and astronomers prefer to express it in the units arc-seconds. In this case, it is just less than 0.7 arc-seconds. It corresponds to a distance of about 1.4 kilometers at the distance of the Moon. This photograph was taken with the celestron telescope. Photographs rarely achieve diffraction-limited quality, but details of 10 kilometers or less are probably detectable. The diameter of the iris of the human eye varies quite a lot. This one is about 4 millimeters. The diffraction limit of resolution for this eye is about 30 arc-seconds. If a telescope is used with a magnification that increases the apparent size of detail below the limit of resolution of the instrument to a size greater than the limit of resolution of the eye, the result is called empty magnification. The image may be larger, but no more detail can be seen. The maximum useful magnification of the celestron telescope is between 40 times and 50 times, but in practice many users prefer to use magnification of 100 times or more to avoid straining the eye to see detail. The principle of limit of resolution applies to instruments working at other wavelengths. This radio telescope antenna has a diameter of 32 meters, and it detects radio waves of wavelength 50 millimeters, so its limit of resolution is in the region of 6.5 arc-minutes. This is much poorer than the unaided human eye, but it is working in the microwave region of the spectrum that the eye cannot see, and, what's more, it isn't used on its own. It's used in a network of similar instruments hundreds of kilometres apart. Together they synthesize a telescope with a diameter of 233 kilometres, which gives the instrument a limit of resolution of a few hundredths of an arc second.